All right, so we're going to talk about probably the three most important concepts in circuits. You can analyze basically any type of circuit as long as there's just batteries, resistors, and switches, uh, and different paths using these three rules. Two of them are Kirchhoff's rules. The one rule is that the voltage in any loop equals the voltage of the battery, or in other words, the voltage in any loop gets used up. Another rule is that the current into every spot of the circuit has to equal the current out of that spot of the circuit. And then we have Ohm's law, which says V equals IR. Now let's go through some examples to talk about what do they mean and how to apply them. So let's start with a real basic circuit here. This is a series circuit. Now before I do anything with the circuit, I'm going to describe what each thing is. So this is a 30 volt battery connected to a 10 ohm resistor and a 20 ohm resistor. And the first thing I want to do is I want to draw with a red marker. I'm going to label the path electricity is going to take. It's going to go from the positive side of the battery around to the negative side of the battery. And we're going to call that current. We're going to call that I1. All right. Well, just because I won. Yay, I won. No, just label it I or I1 because some of these circuits are going to have multiple currents, multiple different paths. This one only has one path, so we always have I1, the entire path. Now, in blue, I'm going to label this loop. Every single loop in the circuit has to use the complete voltage. So from here to there, I'm going to call that L1. That's a loop, right? So now, I'm going to use these three rules. Voltage in each loop gets used up, equals the voltage of the battery. So if I look at L1, what does that mean? What's the voltage of L1? Well, it's going to equal 30. So the voltage in L1 equals 30. Now, where is that voltage being given to? Well, it's going to go around and it's going to be, some of that voltage is going to be used up here, some of the voltage is going to be used up here. So I'm going to set that equal to, that 30 volts has to get used up in two different spots. So some of it's used up here. The amount of voltage that this one uses up is going to equal V equals IR using Ohm's law. Well, I'm going to write down what that is. Now I do know what the R is. The R is 10. And the I don't know what the I is, but I do know I labeled it as I1. Okay. So the amount of voltage that this one uses is I1 times 10. I don't know what I1 is yet, but I can figure it out later. Now, it also has to use up some voltage here, which is, we're going to add that on. It's going to be 20 is the resistance times I1, because IR. So 20 is R, I1 is the current. Okay? So I wrote an equation here for the first loop, for our only loop in this case. I have 30 equals 10 I1 plus 20 I1. I could simplify this equation quite a bit. I could say that 30 is equal to, well, 10 plus 20 is 30 I1, in which case I can solve for I1. I1 is going to equal 30 divided by 30. So I1 ends up being 1 amp. All right, so if the problem asked you to solve for what's the current in the circuit, I'm done. Now, the problem might ask you to extend that a little bit further and ask you for the total power or the total resistance in the circuit. And what you can do then is just make a little verb table. So V, I, R, P. And maybe I'll erase this since we got our work done, VIRP. And basically what you do is I can label this resistor A and resistor B, or resistor A, resistor B. I'll just fill in some information. So I know that resistor A is 10 ohms, and a resistor B is 20 ohms. I know the current for both of them because they both use I1 is 1 amp and 1 amp. So I can use V equals IR to figure out how much voltage they each use. The voltage for this one would be 1 times 10, which is 10. The voltage for that one would be 1 times 20, which is 20. And then the power would just be I times V, P equals IV. So we'd have 1 times 10, which is 10 watts, 1 times 20, which is 20 watts. There we go. We now know the power that each resistor uses, the voltage that each resistor uses, the current that each resistor uses. So if we want to find out what the totals are, we can just add them up. We can add up the power, total power for the circuit, for example. Okay, let's apply Kirchhoff's rules to a parallel circuit. The same rules apply. So here we have a parallel circuit, 10-volt battery connected in parallel to a resistor A, which is 10 ohms, and resistor B, which is 20 ohms. So I'm taking those same two resistors, but now I'm connecting them to a different battery, a 10-volt battery, and then putting them in parallel instead of series. We're going to fill in our VIRT table here too, but the cool thing is we're going to use Kirchhoff's rules again. So the first thing I want to do is I want to label my current. I want to start with a red marker, and I'm going to look at the current leaving this battery. It's going to come here and, oh, now it has a choice. It has a choice when it gets to that intersection. So I'm going to label this I1, and then that intersection, the current's going to split up. It's going to split. Part of that current's going to go down this way, and the other part is going to go this way. It's going to split into two. And they're going to meet back up here at that spot. We'll call this I2, and we'll call this I3. It doesn't matter what you label them as, just make sure you label them something different. So I called it I1, I2, I3, and then they're going to meet back up here at this spot. I3 and I2 are going to meet back up and come back to the battery. Now we know that this, the current leaving the battery is I1, so you know that the current coming back into the battery is also I1. Okay. Now the first circuit, we didn't have to use the current in equals current out rule. It just kind of, because we only have one current. But this one actually comes in handy. So if I do the current in equals current out rule, I'll do that in red. I'll start with that first. I can pick any spot in the circuit. And every spot of that circuit, the current that goes into the spot equals the current that goes out. I want to try to find some useful spots in the circuit. Maybe let's look at this blue spot right here. That's called an intersection or a junction. At the intersection, the arrow going into it, pointing towards that dot, I1 is going into that dot. So I1 is the current going in. That has to equal the current going out, or currents going out. There are actually two arrows going away from the dot. One of the arrows is I3, the other arrow is I2. Those two currents are going away, so they, according to this rule, the current in, which is I1, has to equal the current out, which would be I2 plus I3. Those two currents are leaving that intersection. So the current in is I1, that's the arrow pointing towards the dot, and then the two arrows pointing away from the dot are the currents that are leaving. They have to equal each other. So there's one equation right there. I'm going to put the box around that. Now, I'm going to label my loops. This time I have two loops instead of one. So I'll label this loop right here. This little loop right here, we'll call it L1. I have electricity leaving the battery, making this little loop right here, getting back to the battery. In a different color here, let's make it green. I have electricity leaving the battery, going around this big loop, and coming back. We'll call that L2. And according to this Kirchhoff's rules, the voltage in any loop has to equal the voltage of the battery. So let's look at what that means. Let's look at L1 first. L1. Well, starting at L1, that's the blue loop. What's the voltage? It's 10. 10. Then I go around the loop, and that 10 volts has to equal, well, whatever voltage this is. Well, this was 10 ohms. I know the voltage that this one uses. It's just going to equal IR according to Ohm's law. So I would write down I times R. The R is 10. And the I, turns out that the I is I3. I labeled it as I3. So there is another equation. I can look at loop number 2. Loop number 2 says, all right, loop number 2 is in green. I know that also, there's only 10 volts, because that loop has to equal 10 volts, has to equal the volts of the battery, so 10 volts equals, goes around this loop. This is the only thing that it hits. It doesn't go to this resistor here, because that's not part of that loop. It's inside the loop, it's not on the loop. So this is going to equal I times R. That's the voltage that one uses. The R is 20, and the I is I2. I label it as I2. So look at this. I have 3 equations and 3 unknown variables. Okay? Well, the cool thing is I can solve for some of these variables pretty easily. Let's look at L1. All right? I have 10 equals 10 I3. 10 equals 10 I3. So what's I3 equal? Well, I3 is going to equal 1 amp, because 10 equals 10 times 1. Well, if I look at I3, what thing is using I3? That's resistor A. So based off my picture, that's where a picture is really useful, and these labels and things are very useful. I know that the current going through A is 1 amp. Okay, let's look at loop number 2. Loop number 2 says 10 equals 20 I2. Well, what would I2 be then? It would be 10 divided by 20, which is 0.5 amps. So I2 is 0.5 amps. Well, then I look at loop number 2. I see, hey, everything in I2 is 0.5 amps. Well, then everything that's touching that I2 has to use 0.5 amps. The 20 ohm resistor is going to use 0.5 amps. So that is going to be B, 0.5 amps. Finally, I know that if I wanted to figure out if there was something in I1, let's say I had a resistor in I1 and I want to figure out what that was, well, I can figure out what I1 is too, what the total current is. It would be I2, which is 0.5, plus I3, which is 1, so the total current is 1.5. Well, does 1 plus 0.5 equal 1.5? Yes, that's one way to check your work. Turns out I don't really need that third equation this time, because there's nothing there that's useful, but later on there will be. Well, now I can fill in the rest of the information here. Resistor A is 10 ohms. Resistor B is 20 ohms. All right. Then I can use V equals IR to figure out the voltage. 1 times 10 is 10 volts. And then 0.5 times 20 is 10 volts. And then I can use I times V to get the power. 1 times 10 is 10 watts. And 0.5 times 10 is 5 watts. There we go. Now I know the total power. The total power would just be 10 times 5. But I know the power of each resistor, I know the distance of each resistor, the current of each resistor, and the voltage of each resistor, which is really cool. Now, onto those really tough combination circuits where you have to put things together. The cool thing is, Kirchhoff's rules still apply. So, let's look at our picture here. And the cool thing is, if you use this technique, you don't have to redraw the circuit at all. You just have to be a little bit good at algebra. Okay? So let's start with our currents. The current so you have a 10 volt battery, 10 ohm resistor, 20 ohm, 30 ohm, 40 ohm wired up in this configuration. I'm going to start with the current leaving the battery. It's going to go along this merry way, and it's going to hit this intersection. It's going to split up into 2 pieces then. We'll call it I1. All right? I1 is going to split. Part of it's going to go down this path, and the other part of it's going to go around this path. We'll call this I2. We'll call this I3. So this little dot right here, some current's going into it, I1's going into it, and I2 and I3 are leaving it. Then at this dot right here, that other intersection, I2 are going into it and I3 are going into it, and what's leaving? Well, I1, because the current leaving the battery has to equal the current coming into the battery. That also applies. So it turns out we can actually write 2 equations for this. Let's write them both out here, just for the current rule. So the current rule says, let's pick that spot right there. It says I1 is the current going in, because it's the arrow pointing into it. And there's 2 arrows pointing away from that, and that's going to be the current going out, which is equal to I2 and I3. So I2 and I3 are both leaving, so that rule applies. I can look at the other intersection too. The current going into it is I2 and I3, and the current leaving is I1. So that means that I2 plus I3 equals I1. Actually, you get the same equation. It doesn't matter which spot you pick on the circuit, you get the same equation. So that's good. That tells me some information. I'm going to box that equation right there. Actually, let's move it up here so I have some space. So I1 equals I2 plus I3. We're going to come back to that one because this time we're going to actually use that equation. Last time we didn't need to use it because we got our information from the loops, but this time we're going to, because it's a combination circuit, we're going to have to be using this equation to solve our math. Now, let's look at the loop rules. All right, let's label my two loops first. I'll do that in blue. All right, so I see one loop right here. We'll call it L1, and then next thing I can do another loop too. We'll call that maybe I'll do that in green. Voltage can leave the battery. It can go around this little bit bigger loop, and we'll call that L2. All right. So when I say L1, it's going to basically take this inside loop, and L2 is going to take that big outside loop. I just labeled the inside loop of it. Okay, so L1, let's look at the rules. For L1, we have the voltage in each loop is equals the voltage of the battery, or the total voltage. And this time, the total voltage is 10. So we know that L1 is 10. Now, we have to go around that loop, and we have to basically set the voltage of each thing that uses that voltage in that loop equal to 10. Here's what that means. The first thing that we run into for L1 is just this inside loop. When we go around, we hit resistor A. Resistor A is going to use up some of that 10 volts. Not all of the 10 volts, but some of it. And how much is it going to use? It's going to use I times R. So I wrote down I times R. R is 10. And I is equal to I1. That's the current running through that resistor. It's I1. Okay, but we're not done yet. We're going to keep going around that loop. So we went through this part. Now we're going to go through this part. This is another resistor that's using up some of the voltage, some of that 10 volts. And we know that resistor B is the voltage it's going to use up is I times R. So we're going to add that on. The resistance is 20. And the I that it uses is I3. So we're going to add on 20 I3. And then finally, we're going to try to get back to the other side of the loop here. So we're right here. We're down the bottom here. We've got to complete the loop. And this resistor down here uses up the rest of the voltage. How much is the rest of it? Well, it's going to be I times R. And the R is 40. So we have 40. And the I is I1. Okay. So look at that equation. We have 10 equals 10 I1 plus 20 I3 plus 40 I1. Now, one thing we can do with that equation is we can kind of condense it down a little bit, at least to start. Let's look at it. I don't need the L1 here. All right. What's one thing I could do? Well, I have a 10 I1 and a 40 I1, and they're added together, so I can make that 50 I1. So I'm going to rewrite this. Maybe 10 equals 10 plus 40 is 50 I1 plus 20 I3. It made it a little bit cleaner. It's still not solvable at this point because you have two variables in the equation. It's still not solvable, but it made it a little bit nicer to look at and a little bit easier for us to work with. So now we have two equations. Okay, two equations. Let's look at that last loop. Maybe that last loop will tell us some more information. Okay, the last loop here. Same rules. We know that loop number 2, the big green loop, the big outside loop, we know that's going to equal 10 volts. And that 10 volts has to get used up somewhere. So where does the 10 volts go? Well, it goes to the 10 ohm resistor. And so that's the first thing it encounters. Well, the amount of voltage that the 10 ohm resistor uses is I times R. The resistance is 10. And the current is I1. Okay. Then we go around this bigger loop, not this inside loop, but the bigger loop. We run into resistor C. Resistor C uses some voltage, not all 10, but some of the voltage. We're going to add that voltage on. It's going to be I times R. 30 is the R, and the I is I2. That's the I that current, or that resistor uses. And then finally, we get to the outside part of this. We're going to have I times R for this resistor. That's how much voltage it uses. It's going to be 40 I1 again. That's the current that one uses. We can condense this down a little bit because 10 I1 plus 40 I1 is 50 I1, so I'll do that right now. I'll just make this 50 and get rid of that 40. Hopefully that made sense because it was 10 plus 40, just made it 50. So now we have another equation. So I'm going to put a star next to my three equations. Star, star, star. Now, with this, I didn't have to redraw my circuit. I just had to label stuff. And with these rules, I was able to get three equations. I had three equations and three unknown variables. Three equations, three unknown variables. So what that tells me is that this is solvable. Because as long as you have as many equations as you have variables, you can solve it. It just takes a lot of algebra. So what you have to do then is you have to set things equal to each other and solve for one variable at a time. So how do we do that? Let's look at these two equations right here. It says 10 equals 50 I1 plus 20 I3. 10 equals 50 I1 plus 30 I2. Well, since they both equal 10, since this equals 10 and this equals 10, that means that this equals that. So I can set those equal to each other. So that means that 50 I1 plus 20 I3 equals 50 I1 plus 30 I2. Okay? Well, cool thing is that with this, I just set this part equal to this part because they both equal 10. Now with that, I can start to cancel some stuff out. 50 I1 equals 50 I1, those cancel out. So what I'm left with is 20 I3 equals 30 I2. So I'll write that down over here. Or I could simplify that even more. 2 I3 equals 3 I2. Because if 20 I3 equals 30 I2, then I just divide both sides by 10. And, okay, well, there's another equation here. Which means I don't need this bottom one anymore. All right, so that's one more piece of information I got. What else can I do? Well, I know that I1 is equal to I2 plus I3. So here's an I1 here. I'm going to rewrite that equation up there. I'm going to say 10 equals 50 I1. Instead of saying I1, I'm going to say I2 plus I3. Just replace I1 with I, and then 20 I3. So just a little substitution. Put this in for I1. Now I can factor this into it. So I have 10 equals 50 I2, multiply the 50 in, plus 50 I3, plus 20 I3, which would be 70 I3 total. Okay, so what does that tell us? Well, it tells me another equation that I can work with. And what I can do is say, look at this. I3 and I2, there's a relationship between I3 and I2 right there. Here's a relationship between I3 and I2. What I can do is say, all right, so what's another way to say this? I could say that if I divide both sides by 2, divide this side by 2, I get I3, and divide this side by 2, 3 divided by 2 is 1.5. So this equation tells me that I3 equals 1.5 I2. So anywhere I see an I3, I can replace that with a 1.5 I2. So I'll do that. Times 1.5 I2. We'll look at that. Now I have one variable in that equation. one variable in this equation. I have 70 times 1.5, which is 105. So 70 times 1.5 is 105 I2 plus 50 I2 equals 10. Well, 105 I2 plus 50 I2 is 155 I2. All right. 155 I2 equals 10. So then I2 would equal 10 divided by 155, which is 0.6 amps. So I2 is 0.6 amps. I'll even put a step like I2 is 0.6 amps, and I'll put it there. So anywhere you see an I2, you can put 0.6. So if this is 0.6, what's 0.6 times 30? 0.6 times 30 is 24. All right, look at that. That does simplify things quite a bit now. Oh, look at this. I2 is 0.6. That's why I wrote all these equations up here, because now every single place I see an I2, I can just replace it with a 0.6. So an I2 is a 0.6. 0.6 times 1.5 is, I think it's 1. Sorry, it's not 0.6, it's 0.06. My bad. 0.06. 0.06. 2.4. And 0.1. Oh, sweet. So now I have a variable that says I3 is 0.1. So if this is I3 is 0.1, then this is going to be 2, because 0.1 times 20 is 2. So now we're just kind of going through each equation and filling in what these things are. This would be 0.1. Look at that. You just find the equation that you want. 0.06, 0.1, this is going to be 0.16. Look at that. And I could go through and double check all these equations to make sure that they work out. But all you need is one of them to tell you what I1, I2, and I3 are, and it works. So that's the cool thing about these. So you have to set things equal to each other. There's no particular order you have to do that, as long as you can find things you can set equal to each other or substitute in. It takes some algebra skills, but it's either this or redrawing the circuit a bunch of times. It's up to you. So now, with this, I can just replace all of my, I know my resistances. A is 10, B is 20, C is 30, D is 40. Okay. Then for this path right here, 10, what is it? It's I1. I just have to write down what I1 was. I1 was 0.16. Yep. So this is 0.16. For the 20 ohm, it's I3. I have to write down whatever I3 was. I3 was 0.1. All right. Then for C, I have to put down whatever I2 is, because that's what I2 is. It's using. I2 was 0.06. And then for 40, I can use I1 again, because I1 was the path that it took, and 0.16. Oh, look at that. I now know enough information to fill in the rest of the verb table. I can use V equals IR to get V, so 1.6. And then 0.1 times 20 is 2. 0.06 times 30 is 1.8. And then 0.16 times 40 is 6.4, I believe. Then I can use P equals IV to figure out the power. I won't do that. As long as you get VIR, that's going to tell you enough information. PIV is going to be one more step that you can do. All right, the last type of circuit that could be thrown at you is if you have multiple batteries. And not only that, but multiple batteries, but in different locations of the circuit. It makes it a little trickier, but not too bad. I don't think it's as hard as combination circuits. Okay, so what you do is the same rules. All right, here I have a 10-volt battery, resistor A, B, and C, and a 12-volt battery over there. And the direction of the battery is oriented also matters, so pay attention to that. But I'm going to still follow the same rules. So the first thing I'm going to do is I'm going to look at this battery right here, and I'm going to say, all right, that current is leaving this battery, and then it has a choice. It can go this way or it can go this way. So some of it's going to go this way, and the other part's going to go that way. So we'll call this I1, also call that I1 because the current going into the battery equals the current going out. We'll call this I2. Now, this battery over here is also going to push electricity out. It's going to push it this way. We'll call it I3, and then likewise, it's going to split up. Part of it's going to go this way. The other part's going to go down this way, I2, and then it's going to go back to I3 because the current leaving was I3 and the current coming back in has to be I3. So with this one, we actually have like 3 loops in the circuit. I'll show you what those loops are in a second, but let's look at the current rule first. Here's a little intersection. Here's an intersection. That intersection says that I1 is going in, I3 is going in, and I2 is leaving. So the current's going in, I1 and I2. Those are the currents going in. They're both pointing towards that dot. And then I3 is leaving, so that's the current going out. We could look at this dot right here, and I1 and I3 are leaving. Sorry. I1 and I3. Oh, my bad. I1 and I3 are going in, and I2 is leaving. My bad. All right, so you got that. I1 and I3 are going in, I2 is leaving. Down here, I2 is going in, and I3 and I1 are leaving. So you get the same equation whether you look at it either way. So we have our current rule equation. All right. So now we're going to look at our loop rules. So actually we can draw 3 different loops this time. The first loop we can draw is this battery, which goes around this way. That'd be loop 1. I can draw another loop with this battery. That's loop 2. And then I can draw another loop around the whole circuit. And that'd be loop 3. And you know what? I'll do that. I'll draw a loop maybe from, it doesn't matter which direction you go, because you still follow the same rules. So I'll maybe start over here and go around the whole entire battery, and we'll call that loop 3. Turns out we only need 2 loops to analyze this. Drawing that third loop is redundant. It'll give you more information, but you don't necessarily need that information. But we'll still go with it. Let's look at one loop at a time. Loop number 1 is labeled here. And so it says the voltage rule says that the voltage equals 10, which equals, well, the first thing it meets is this resistor right here. The amount of voltage that one uses is not 10. It's going to be part of that 10. It's going to equal I times R. Well, the R is 10. And the I that it uses is I1. We labeled it as I1. We're going to keep going around that loop. This loop right here, its resistance is 6, and its current is I2. So it's going to use 6 I2. That's how much voltage it's going to use. Then we get back to here. There's nothing in this path right here, but if there was, we would just do something times I1 because it's the current that I would use, but there's nothing there, so we could do 0 times I1. If you could write that if you want to. Back to that. Well, there's one equation. All right. Let's look at loop number 2. Loop number 2 is 12 volts. So this is going to be 12 volts. We go around this path. The first thing it runs into is this 8 ohm resistor. So it's going to equal I times R. The I is I3 and the R is 8. So we have 8 I3. We go around. Oh, sweet. It's going to go around this path right here. That's the loop. And so it's going to add on 6 times I2. That's the voltage that it would use, I times R, so 6 I2. And then it goes around this loop. Once again, there's nothing there on the bottom, so we don't have to worry about it. That's our equation here. And then finally, if we want to do that big loop, we don't have to. It just tells us more information. The big loop, we would start with 12, but then we have another voltage over here, 10. Now, one battery is pushing electricity this way. The other battery is pushing electricity this way. This one's 12, this one's 10. It's almost like a tug of war. It's almost like a force, a net force equation. Basically, instead of having a 12 and a 10, what we can do is to say there's 2 going this way. There's 2 more going this way than this way. So I can just imagine that battery's not there for that big loop and just say that this is a 2-volt battery. So basically, you're writing your net voltage. Net voltage. If there's batteries fighting against each other, then you subtract them. If this battery was facing the other way, then I would add them together because they're both pushing the same direction. They're like pushing and pulling. We have one pushing this way, one pushing this way. This one's pushing a little bit more. So we're going to have the total voltage in this big loop is equal to 2. Hopefully that made sense. Because it's 12 minus 10, because they're fighting against each other, which equals 2. So the total voltage in that big loop is 2. Well, 2 equals, now I just look at everything on the outside, it's going to equal 8 times I3 plus 10 times I1, and then that's it. That's it. So now I'm going to write that last equation over here on the side because it turns out that that one is the least useful. It's maybe just one to double check our work. A lot of times we don't bother with the biggest loop. We just need 2 loops. And it just ends up being more equations to work with. So I am going to erase that one. I'll write over here just in case we want to use it to double check our work. Or if we get stuck with the algebra. Okay? So now, what we need to do is we want to solve for I1, I2, and I3, because then we can fill in the rest of this table. I didn't write the P here. Let's fill in the resistances first. So resistor A is 10, resistor B is 8, and resistor C is 6. So if I can find the I's for each one, then I can find the voltages and powers. Just use V equals IR and P equals IV. So once I find I's, I'm essentially done. Then it's just plug chug, right? So to find the I's, it's going to take some algebra. Well, I have 3 equations and 3 unknowns. Actually, I have 4 equations and 3 unknowns. I don't need 4. I only need 3, which is why I have this other one just as a double check. So let's see what we can do. All right, so I'll write this equation up here. So we have our 3 equations all right in a row here. I1 plus I3 equals I2. So here's our 3 equations, our 3 unknowns. What you want to do is you want to try to simplify them by combining them and see what we can do with that. Now, this equation has an I1 and an I2. This equation has an I3 and I2. It'd be nice if we could, like, I don't know, like get everything in terms of I1 and I2. Get rid of the I3 completely. We don't want it. We want to get rid of it. So what is I3 equal to? Well, I3, according to that first equation, I3 is going to equal I2 minus I1. If you don't see that, what you do is subtract off I1 from both sides. So I3 is equal to I2 minus I1. So anywhere I see an I3 in any of these equations, I'm going to write I3, I'm going to write I2 minus I1. So with this equation, I get I3 is equal to I2 minus I1. This one doesn't have an I3 in it, but this one does. So I'm going to replace it with I3, or I2 minus I1. So down here, let's rework that third equation. See if we can clean it up a little bit, and see what we can do with that. So now we have 12, that didn't change, equals 8I2 minus 8I1 plus 6I2. So 8I2 plus 6I2 is 14I2. So now what I'm going to do is I'm going to replace this equation. I don't want that equation anymore. I don't need it. All right, I'm going to replace it with this one because it's the same thing. All right. So that equation I'm going to just rewrite here. So 12 equals 14 I2, actually, yeah, minus 8I1. Okay, so now if you look at these two equations right here, I have two equations and two unknowns. Okay, that's a little bit nicer because I got rid of that I3 completely. I don't need it anymore. So now I need to figure out two equations, two unknowns. What I'm going to do, it'd be nice to set these two equations equal to each other, but I can't because this is equal to 10, this is equal to 12. But the cool thing is, both 10 and 12 both go into 60. That's the least common denominator between them. So I want to do that. I want to multiply this top equation by 6 so that I get to 60. So I multiply the top equation by 6, I get 60. If I multiply this side by 60, I get to multiply this side by, sorry, multiply that side by 6, I get to multiply this side by 6. So if I multiply this side by 6, I get 6, and then I get 36. Okay, so I didn't really change that equation. I just multiplied it by 6, everything in the equation by 6, and it still holds true. I'm going to do the very similar thing to the bottom equation here. I'm going to multiply everything by 5. If I multiply the 12 by 5, I get 60. If I multiply the 14 by 5, I get 14, 28, 42, 56, 70. And then if I multiply 8 by 5, I get 40. Now that's just a trick that I know what to do for algebra, is setting equations equal to each other. But if they don't equal each other, you just find a way to get them equal to each other, like finding the least common denominator, something like that. Now I could have just did some more substitution and solved it that way because I had two equations, two unknowns, but I'm just showing you one trick. Okay, so now since both of these equal 60, that means that since this equals 60, and since this equals 60, I can set these two equations equal to each other. So let's do that. We have 60I1 plus 36I2 equals 70I2 minus 40I1. All right, so now let's group all the I1s together, all the I2s together. So I1 is 60. I would add on 40 to this side, so I have 100 I1. That gets rid of this 40 over here. And then the I2, I would have 70 minus 36. I believe 70 minus 36 is 34. So then we have 100 I1 equals 34 I2. I could divide both sides by 34 and get 2.94. So I get 2.94 I1 equals I2. All right, so 2.94 I1 equals I2. Maybe I'll just do that. Okay, so now I have an equation up here. Let's look at it. I have 60. I can pick either one of these equations at this point to solve for it. I have 60 equals I1. Okay, so I have 60 I1 plus 36. Now, I don't want to write I2. I want to get everything in terms of one variable, I1, for example. Well, instead of writing I2, I can write down 2.94 I1 because they're equal to each other. 2.94 I1. And look at that. Now I can multiply 36 in. So now if I multiply 36 in by 2.94, I get 106. Because 36 times 2.94 is 106. 106 I1 plus 60 I1 is 166. So then I can add these together. 60 plus 106 is 166 I1. So I'll do that. 166 I1 equals 60. And now, look at that. I solved for I1 because 60 divided by 166 is 0.36. So I1 is 0.36. So 0.36. I1 is 0.36. I1 is 0.36, and look at that. We have more than enough ways to get I2 and I3, okay? Now, I gotta just multiply this in by 0.36. I would solve for I2, or I can do the other thing, multiply by 0.36, solve for I2. There's two different ways to check my work. Then once I get I2, which ends up being, I believe I did the work already, 0.7? No, I3 is 0.7. I2 would be 1.06. Then I can get I3, which would be 0.7. And indeed, you can double check that work if you want. But basically, there's lots of different ways to solve these different types of algebra problems. What you have to do is set equations equal to each other. Do substitutions, set equations equal to each other. And, and the rules just go to work at that point. So then you would just fill in the VIR table. You'd have all the currents. A would use I1, B would use I3, and C would use I2. It's arbitrary how you label them. That's why a picture is useful. You'd use V equals IR to figure out the voltage, P equals IV to find the power, etc. So it ends up being a lot of algebra, but it's one alternative to drawing a lot of different circuits and then piecing together a puzzle. You can do multiple different ways to solve these different circuits. But as long as you remember Kirchhoff's two rules and Ohm's law, you can tackle basically any circuit possible, as long as it's just resistors and batteries. If you throw capacitors in there, then the rules still apply, but we'll just have to do something else with them. It actually becomes a little easier, but we'll talk about capacitors later. But anyway, that's it. That's the hardest part, I think, is analyzing these circuits. But it can be kind of fun once you get some practice down. So